This podcast is on solving nonlinear systems of equations. In the past, you've already solved linear system of equations. Just to review that quickly, I've put a system of two equations with two unknowns. It's called a linear system because each one of the equations here represents a line, and I've taken the liberty of going ahead and graphing the two lines here. This line over here that slopes upward to the right is x minus y equals 2, and the other line is 2x plus y is equal to 4. Now when you graph a linear system like this, the solution is where the two lines cross. These lines cross 2 to the right and none up, so that's the point 2, 0. So from the graph, we would read the solution of this system as being 2, 0. But usually on graphs, you can only get approximate solutions. So what you try to do always is solve algebraically. If you look over to the right, you can see the algebraic method of solution. I've rewritten the system here just as it was before, and we solve it by what's called the addition method. In this case, I add the two equations up and I get 3x plus 0 equals 6, so x equals 2. Now x equals 2 can't be a solution. It can't be a solution because this is a two-variable equation. You need a number for x and a number for y. So I go back into the second equation. I put x equals 2, so now it says 2 minus y equals 2, and that tells me y has to be 0. I get the solution 2, 0. That's the same solution I got where the lines crossed. So in general, you do not need the graph to be able to solve these systems. Now let's take a look at some nonlinear systems. In nonlinear systems, like in example 1, at least one of the equations must not be the equation of a line. So if you look at this first equation here, that's our standard parabola, y equals x squared, and it's got a vertical shift of 1 unit. So it's y equals x squared lifted up 1. Now, as I said, you don't need graphs to solve these, but in this first example, just to give a feel, I'm going to go ahead and graph this anyway. So it's a standard parabola lifted up 1. So its vertex will be here. When I move over 1 from the vertex, I move up 1. When I move over 2 from the vertex, I move up 4. And since it's symmetric, and since the line of symmetry goes through the vertex, which is on the y-axis, that means the y-axis is its symmetry line. So I'll get another point here, and from the symmetry line, I'll get another point here. And so my parabola is going to look like this. Now, let's take a look at the second equation, which is the equation of a line. To make it a little bit easier to graph, I'm going to move the y to the right, where it'll become a positive y. And I'm going to move the 1 to the left, where it'll become a positive 1. And I get the equation y equals x plus 1, which tells me the slope is 1, which is 1 over 1. And the y-intercept is 1. Well, if the y-intercept is 0, 1, that's right here at the vertex. So that gives me my first solution, 0, 1. Now, if the slope is 1, that means for another point on the line, I move over 1 and up 1. Well, that gives me a second solution, because that's also on the parabola. That's 1, 2. And the line, of course, looks like this. It will be just a straight line through those 2 points. And it's hitting the parabola at 1, 2 and at 0, 1. So those should be our solutions. But as I said, you do not need graphs to solve these. In general, you're going to solve them without reference to a graph. All you need is the equations and your algebra skills. So let's go ahead and solve this first one. We saw down here that y was x plus 1. We got that from equation 2, so we'll substitute it back to equation 1. Where I have a y on the left, I'm going to replace it with x plus 1. So that's going to say x plus 1 is equal to x squared plus 1. Now, to continue on, I want to try to solve this by factoring if I can. That would be the easiest method, so I'll subtract x and subtract 1 from both sides. So on the left, I'll have a 0, and on the right, I'll have x squared minus x plus 0, so I get 0 equals x times x minus 1, and my two solutions are x equals 0, x equals 1. But I can't say that a solution to this system is 0, 1. A solution to the system has to be a pair xy. 0, 1 is a pair xx. They're both x's. But I can use the x to find the y. So if I take my x equals 0 from my first solution and I plug it into my equation, I get 0 plus 1 is y, so y is 1, and that corresponds to that solution. If I take my 1, my second x, and I plug it into the equation, I get 1 plus 1 is y, so y is 2, and there's my second solution, and there is my solution by a totally algebraic means. In the last example, these two equations represent figures called hyperbolas that are a little bit beyond the scope of our course, but let me say if we saw the graphs, we would see that there are only three possibilities here. Either this system has no solution, or it has two solutions, or it has four. Now, we don't need to know that to solve. All we need to solve is to do our algebra. Normally when we do our algebra, we either solve for x or solve for y. In this case, though, we could take a big shortcut by solving for y squared. So I'm going to do that in the second equation, and you'll see quickly how that works out. To solve for y squared, I'm going to move my y squared term to the right where it becomes positive y squared, and I'm going to move 2 to the left where it becomes a positive 2. So I'll get 2x squared plus 2 equals y squared. Now I'm going to substitute that into equation 1. So I'm going to write equation 1 with empty holes, but not an empty hole for y because I didn't solve for y. I'm going to put an empty hole for y squared because that's what I solved for. So this was negative 2y squared, so I write negative 2 empty hole equals negative 5. And into the empty hole goes what I got for y squared, which was 2x squared plus 2. Now I simplify by distributing. Minus 4x squared minus 4 equals negative 5. And I combine my like terms, which gives me negative x squared. And that looks maybe factorable, so I'll bring my 5 over to this side where it'll become a plus 5, so that'll make that a plus 1 equals 0. And now I'm going to factor out a negative 1 to give me the very familiar form of a difference of squares, x squared minus 1 equals 0. Now I could get rid of the negative by multiplying both sides by negative 1. That would make this positive, and that would still be 0. And then I get the solutions x equals 1 and negative 1. Now negative 1 is not a solution to this system. I can't emphasize this enough. 1 and negative 1 are both x's. A solution is not in the form xx, it's in the form xy. So what we have to do is we have to take our first x equals 1, and find the y's that correspond to that. Now to do that, I'm going to go here. If x is equal to 1, and I want to know my y's, I put a 1 in here. So 1 squared is 1. 2 times 1 is 2, plus 2 is 4. So I get 4 equals y squared. By the square root property, that tells me y is positive or negative the square root of 4, which is positive or negative 2. So corresponding to the x value 1, I get y equals 2, and I also get y equals negative 2. So that's two solutions. Now I want to see if any solutions correspond to negative 1. I go right back to my solution for y squared, and I plug negative 1 in. But if I square negative 1, I still get 1. So 2 times 1 is 2 plus 2 is 4. I still have y squared equals 4. So y is still positive or negative 2. So corresponding to negative 1, I get the two solutions negative 1, 2, and negative 1, negative 2. We said in the beginning we should have either 0, 2, or 4 solutions. Here are our 4 solutions, and that completes the podcast on solving nonlinear systems.